Good morning. I hope you're doing well. So today we'll talk about graphs of polynomial functions, and we'll talk about this tomorrow as well. Now, a polynomial function is one that has a continuous and smooth curve. The curve is continuous and the curve is smooth. Continuous and smooth. If it is continuous but not, if it is smooth but not continuous, because this here is smooth, that section is smooth, but this part is not continuous, then that's not a polynomial function. And if straight up it's not smooth, because that's not a smooth edge, then it is not a polynomial function. Now, polynomial functions, just like any other functions, will have intercepts, x-intercepts, y-intercepts. To find the x-intercepts, and just a reminder, an x-intercept is the point where the function cuts the x-axis, and that point is where the y value is equal to 0, because the x-axis is the same as the line y is equal to 0. So to find the x-intercepts, I simply need to equate f of x to 0. If I set f of x is equal to 0, then I can solve for the x-intercepts. Now, when you look at this expression, you see that I have even powers, even power, and I also see that x squared is common. So when I factor out x squared from x to the power 6, I'm left with x to the power 4. If I factor it out from 3x to the power 4, I'm left with 3x squared, and from this I'm left with a 2 is equal to 0. Now, I don't know if you see it, but what I have inside here is a quadratic equation in terms of x squared. It can be easier to see if I introduce another parameter. If I say, for example, let x squared equal to p, then in the place of x squared, I will just substitute for p. So that will be, and that substitution is only going to happen inside the parentheses, so I can factorize it easier. So in the place of x squared, this is going to be p squared, because it is x to the power 4. If x squared is p, then this is going to be p squared. This is 3x squared, so it will just be 3p, because 1x squared is a p, and then plus a 2. The advantage of doing that is that it gives me an expression inside which I can easily factorize. So I'm still left with x squared on the outside, but on the inside I have a quadratic expression in which the factors here are 1p and 1p, and the factors here are just 1 and 2. So I can see that if I multiply 1 times 2, I get positive 2. But if I add 1 plus 2, I do not get negative 3. In order to get negative 3, these have to both be negative. Since I can see that negative 1 times negative 2 is positive 2, and at the same time negative 1 plus negative 2 is positive 3, I know that my factors are found, so I can use this idea to combine them. So my factored expression of what's inside the bracket is going to be p minus 1 into p minus 2. Now remember, I introduced that just for convenience. I need to go back to my original statement, my original variables, which was x squared. You know, p stands for x squared, so this is just x squared minus 1, and this is x squared minus 2. So all of this is equal to 0. My factored expression is now x squared into x squared minus 1 into x squared minus 2 is equal to 0. And if I want to find the x values for that, I'm just going to solve by equating each of these to 0. So I'll equate x squared to 0, and I'll get x is equal to 0. Then secondly, I'll equate x squared equals 1. X squared minus 1 equals 0, which if the 1 moves over, I have x squared equals 1, and x is equal to plus or minus 1. And then finally, if I equate x squared minus 2 is equal to 0, the 2 moves over, so I'll have x squared equals 2, take square root, x equals plus or minus square root of 2. So I hope you can see that these are 2 x-intercepts, this is another 2 x-intercepts, and this is 1 x-intercept. That's a total of 5 x-intercepts. Is it consistent with what I expect? Yes, because on a polynomial function, if the degree is 6, then the x-intercept cannot be more than 6 minus 1, cannot be more than the degree minus 1. So this one has 5 x-intercepts. That's what I expect, since the degree of the polynomial is 6. So those are the x-intercepts of this polynomial. If I want to find the x-intercepts of this one, same idea. I'm going to get t cubed minus 5t squared minus t plus 5, and I equate that to 0. Now, remember we are factorizing. So what I did earlier was factor out a common term. Here I don't have a common term, but I can see sort of a common pattern. I can see something that I can use. If you look at this critically, t cubed minus 5t squared and then t plus 5, I can use factorization by grouping. So I can group from these two. I can take out t squared, and then I'll be left with t minus 5. And from these two here, I can take out negative 1, then I'll be left with t minus 5. Because if the negative 1 goes inside, it will give me negative t, and if the negative 1 multiplies the negative 5, it will give me positive 5. So by grouping, I have t squared minus 1, and then t minus 5 is all equal to 0. Again, I can solve by equating each of these parentheses to 0. So if t squared minus 1 is equal to 0, that means t squared is equal to 1. That means t is plus or minus 1. And the second one, if t minus 5 is equal to 0, the 5 moves over, so that means t is equal to 5. For this one, I have a total of 2 and 1, so that's 3 intercepts, which is that consistent with what I expect for this expression? Yes. Wait, was this t squared minus 1? Yeah, that's consistent with what I expect. So that's how you find the x-intercepts of an expression like this. We just check this again. So t squared minus 1, t squared is common, minus 1. Yeah, okay. So how do I find the x-intercepts of this expression? Now, if you look at this one, we know the x-intercepts. Just taking it back a little bit, if I had an equation like x minus 2 squared, this is y is equal to x minus 2 squared, I can see very clearly that if you equate this to 0, the x-intercept is going to be 2. It cuts the x-axis at 2, because that's easy to equate because it's already factorized. Now, the other thing that I also know is that if I substitute 2 into this equation, the value of y must be 0. So if I substitute 2 for x minus 2 squared, the value of y is 0. That's another thing that helps me prove that it is an intercept. Now that trick is useful because there's some equations like this one that are not going to be factorable. It's not easy to factor this using the methods that we know now. So one trick you can use is try and error. You can start with the values between negative 3 and positive 3. You can start with 1, negative 1, substitute them in, and see whether the value of the function is equal to 0. If it is equal to 0, you have proof that it's an intercept. If it is not, you keep looking for another one. However, a straight approach to solve this would be to graph it and check for the intercepts. Well, let's just pretend for a minute that we can't use our graphing calculators or Desmos. Then, to find the x-intercepts, I'm going to do try and error. So I'm going to say, I'm going to try values from negative 3 up to positive 3 on the x-axis. So I'm going to start with the simple one. I'm going to start with 0. If I set x is equal to 0, then h of 0 is equal to 0 cubed plus 4, 0 squared, plus 0 minus 6. That gives me a negative 6. So this is not an intercept. X equals 0 is not an intercept. Not give up. I'll try h of 1. If I substitute x for 1 for x, I'll have 1 cubed plus 4 times 1 squared plus 1 minus 6. Does that give me 0? Yes, this is 1 plus 4 plus 1, which is 6, minus 6. That gives me 0. So that tells me that x equals 1 is an intercept. So since this polynomial is of degree 3, I should expect at least at most 2 intercepts. So I'm not going to stop searching. I'm going to go on to the next one, which is 2. I'm going to try 2. If I put 2, I'll have 2 cubed plus 4 times 2 squared plus 2 minus 6. 2 cubed is 8, 4 times 4 is 16, 16 plus 2 is 18, 18 minus 6 is 12. That is not an intercept because it doesn't equal 0. I'm going to try 3 just for the kicks, but I can see from this trend that 3 won't give it to me, but I'll just try it. 3 cubed plus 4, I'll just try it for your viewing pleasure. 3 squared plus 3 minus 6, this is 27. This is 9 times 4, which is 36, plus 27, big number. I can see clearly by peeking into the future that that's not going to give me an intercept. So since I've tried 0 to 3, I'm going to go to the other side of the x-axis. I'm going to try -1. So that's -1 cubed plus 4, -1 squared plus -1 minus 6. -1 cubed is -1, -1 squared is 1, times 4 is 4, minus this -1, that's a 3. 3 minus 1 is 2, 2 minus 6 is -4, that is not an intercept either. I'm going to try another one, -2, substitute -2 cubed plus 4 into -2 squared plus -2 minus 6. So this is -8 plus 16, which is +8, minus 2, which is +6, minus 6, which is 0. So I can see that this is another intercept. Now since I expect 2 intercepts, because this power is 3, I can safely stop here. So I found my intercepts by trial and error. Some of you might think it's hectic, but if you can't use a calculator, and since we haven't yet learned how to use the remainder theorem to solve this is something you'll learn in the future, then this can be a good approach. So your intercepts are x is equal to 1, because this is the value of x that gave me a value of y of 0, so x equals 1, and the second x-intercept is x equals -2. Now if you are allowed to use calculators, you can just go ahead and graph this expression. If you graph this expression, it shows you right away what the x-intercepts are. So you have +1, which we found -2, and then I should have kept going because looks like -3 was also 1. Just to clarify, I might have misled you. If the highest power is 3, that's the number of x-intercepts it has, but the number of turning points is 1 less than the highest power. So I know I misspoke at some point, but yeah, so the number of turning points is 1 less than the degree of the polynomial, but the degree of the polynomial is at the same time the number of x-intercepts that polynomial has. Maybe just for enjoyment or satisfaction, you can substitute -3 in this in your trial and error, and I'm pretty sure that it will give you 0. So yeah, these are our intercepts: -3, -2, and 1. Multiplicity of a polynomial is the number of times a given factor appears in the factored form of the equation of the polynomial. What do we mean? If you have an equation like this, x plus 3 power 1, x minus 2 power 2, x plus 1 power 3, the x-intercepts, remember you get the x-intercepts by setting this expression equals 0. I can see that when you set x equals 0, expression equals 0, you'll get x equals -3, x equals 2, and x equals -1. So the first x-intercept is -3. Its multiplicity is 1 because the factor x plus 3 appears only once in the factored form. It has a degree of 1, that's why its multiplicity is 1. The second x-intercept is +2, its multiplicity is 2. Third one is -1, and its multiplicity is +3. So you can use your calculator and look at how the multiplicity affects the graph and what it looks like. So you can write different equations, x minus something, x plus something, and then graph it just to see what the graph looks like and how the multiplicities affect how the graph looks at the x-intercepts. So when you do that, you will find a pattern, and if you try equations like x to the power 2, x to the power 3, x power 4, I mean, if you, for example, we're just changing the degrees here, the polynomials, I mean the values of the degrees on each of these factors, you will find that every time the factor is even, the graph will just touch the x-axis. I hope you can concur with this. I hope you used your calculator to test this out, and you'll find that every time because at x equals 4, some clarification, at x is equal to 4, the power of that intercept, the power of that factor is even. If the power is even, you'll find that the graph always touches the x-axis. Let me show you this on Desmos. If the power is even, if the power is even, so if I have x plus 2 squared, the graph will touch the x-axis. Even if this is multiplied by x minus 3 cubed, so for squared, at this point, x equals negative 2, because the intercept of this factor is negative 2, which is right here, the graph touches. But when it is odd, when the power is odd, at that intercept, the graph cuts the x-axis. So this is a pattern you'll see. If the multiplicity is 1, then at that point, the graph will go through the x-axis. If you see this multiplicity is just a power of 1, it's just a power of 1, and at this intercept x is 1, at that intercept the graph just cuts through, right? It just cuts through linearly, because you see it looks like a straight line. And then at this point where you have so this is the factor that has a squared term, where it touches the axis sort of looks like a quadratic graph. And then at the factor where it has a linear term, at the factor where it has a power 1, which is a linear term, which is this one here, the graph just cuts through. And then at the factor where it has a cubic term, the graph looks like a cubic function out from the parent graph function. I hope you remember this. So that's what's going on. At x equals negative 2, because negative 2 is this intercept and it corresponds to an odd power, the graph will cross the x-axis. So that's what we have. You can try this on your graphing calculator and verify it yourself. So at even multiplicity, this is what I was talking about. The graph touches the x-axis, and at odd multiplicity, the graph crosses the x-axis. So we can, an example is here. If I want to use the graph to write the formula for a polynomial function of least degree. Okay, so when I look at this right here, since it is touching, I know that since that intercept is x equals negative 1, its factor, the factor is x plus 1, because the 1 moves over that way. And since it is touching, its power has to be an even power, which is a squared function. I can see that it also touches right here, right? And if it touches in that format, what that means is that it is a linear factor. Since that intercept is x equals 2, I know the factor is going to be x minus 2, because the x moves over that way. Now, this can be one of my polynomials of least degree. But if I want to be very specific, I'm going to add a negative, because I can see that this point has a downward looking shape right here, a downward looking shape, and that tells me that this expression is going to have a negative. Now, I probably know this intuitively because I'm teaching this to you, and I've seen lots of graphs that look like this. Without the negative, you would still have a correct expression, which is of least degree, but just specifically the negative tells me that that graph will have that shape. And you can test this on ThinkWeb, Desmos, or your graphing calculator just to see whether you're right. If I want to use the graph to identify the zeros and the multiplicity of these zeros, well, the first zero is right here, starting from left to right. X is equal to -4. I can see that that zero has a multiplicity of 1, because when the curve touches the graph at this point, it's sort of a straight line, it's sort of a linear expression, so it has a multiplicity of 1. So this factor would be x plus 4 to the power 1. I can see that the graph also touches right here at x minus 2, x is equal to -2. That factor will be x plus 2, because again the 2 goes over there to make a factor. If I write it as x equals -2, that's a solution or a root, but if I write it as x plus 2, that's a factor, because if I equate this to 0, then it's going to give me back x equals -2. And it also has a multiplicity of 1, because how it cuts is a straight line. I have another intercept here, which is x is equal to 3, which means that the intercept is the factor is x minus 3, and since it is touching, not cutting, since it is touching, I know it has a multiplicity of 2. So that's multiplicity from graphs. We'll continue more on this lesson tomorrow. This is your homework. I hope you can enjoy.